In 2019, ASML finally shipped the first high-volume EUV system, completing a long and winding road stretching multiple decades. The move completed the semiconductor lithography industry's shift away from Asia towards Europe. It was a particularly big loss for the Japanese. Japan discovered EUV. Japanese companies led the lithography industry before ASML came along, but they were not able to get EUV out in time. Japan's failed EUV development journey is fascinating, as it illustrates the incredible challenge of producing commercial-ready EUV systems. In this video, we're going to look at Japan's attempt to achieve EUV. But first, let me talk to you about the Asianometry Patreon. Early access members get to watch new videos and see selected references for them before they are released to the public. It helps support the videos since views are so volatile. I appreciate every pledge. Thanks, and on with the show. As I mentioned, EUV was invented in Japan. In 1986, Dr. Hiro Kinoshita, then working at NTT, announced that he had successfully printed a circuit pattern using EUV light and a reflective optics system. A great achievement, but at the time, EUV was just one of several possible next-generation lithography candidates. Others included electron beam direct right lithography, proximity X-ray, ion beam projection, electron beam projection, and 157 nanometers fluorine. The Japanese lithography industry studied all of these, but EUV was not their main preference. They seem to have been leaning towards proximity X-ray, which was what most early progress reports focused on. The Japanese were not alone in this assessment. The Department of Energy's early EUV project was ending without industry follow-up, and as late as 1997, Sematech had evaluated EUV in fourth place, with X-ray again in first. But the American semiconductor leader Intel saw demonstrations in Japan and the Department of Energy labs and liked what they saw. So, with the DOE EUV project R&D team on the verge of being disbanded, they provided bridge funding to keep the team together. And a year later, Intel and other American semiconductor manufacturers founded EUV LLC, an industry-wide consortium to help provide the estimated $60 million a year of R&D to commercialized EUV lithography. Intel's interest in EUV and EUV LLC's founding caught the Japanese by surprise, and unfortunately, due to American restrictions on foreign participation, long geopolitical history there, Japan's lithography makers Nikon and Canon could not directly join EUV LLC themselves. However, they were allowed to participate in design reviews and working groups. The Japanese had to rapidly pivot and go their own path. In 1998, a year after EUV LLC's founding, Japan's Ministry of International Trade and Industry, or MITI, began its own EUV lithography program. As originally planned, the Japanese EUV lithography development plan had 3 phases. In the first phase, we need to develop the basic technologies behind EUV lithography and its 3 system parts: the exposure tool, the mask, and the resist. This would go from 1998 to 2001. The government-funded research organization in charge during EUV Phase 1 was the ASET EUV Laboratory. ASET stands for the Association of Super Advanced Electronic Technologies and was a multi-year research consortium fully funded by MITI. In the second phase, another organization would take over to turn ASET's raw technology into a working prototype. Japan's semiconductor industry would contribute partial financial support here. This second phase would span 3 years from 2001 to the end of 2003. It was not exactly clear at the time, however, who would spearhead this part of the process. Finally, the third-year phase takes us into 2006. This is when the Japanese semiconductor industry would turn that prototype into a commercialized product. Presumably, SELIT, as well as the Japanese lithography makers Nikon and Canon, would be in charge of this. SELIT, or Semiconductor Leading Edge Technologies, is a Japanese R&D research consortium. Their $90 million annual budget is funded by industry, so they focus on more applied technologies. ASET had a formidable task ahead of it. I've done a few other videos about the 3 basic systems within the lithography machine. That includes the exposure tool, the mask, and the resist, and what they do. But let's get a quick recap to get everyone up to speed. The exposure tool contains an EUV light source and an optic system. It fires high-powered light, which then reflects off the mask, which has the chip design printed onto it. The patterned light then falls onto the wafer, which is coated with a photosensitive chemical known as the resist. The resist reacts to the light so that we can use it as a stencil to later etch the wafers. While the EUV lithography machine's three basic systems still shared a philosophical heritage with its predecessors, the actual engineering required brand new substantial work and resources were limited. For the exposure tool, ASET needed to develop the basic technologies behind a large variety of the tool's subsystems. This not only includes the light source and the light optic subsystems, some of EUV's most charismatic parts, but also some less sexy yet nevertheless vital bits, like the mechanical wafer and mask alignment technology subsystem, which aligns the wafer and the mask within tolerances of half a nanometer, and the optics metrology subsystem, which measures the mirror's performance during the exposure steps. Faced with hard choices, ASET chose to focus their limited resources on optics manufacturing, like the work of adding the mirror's reflective multilayers and cleaning them, as well as metrology. ASET choosing to work on the optics meant that it could not work on the exposure tool's light source, an essential piece of the puzzle. This task was reassigned to a new industry organization founded in 2001, the Extreme Ultraviolet Lithography System Development Association, or EUVA. The organization included both academia and industry. 5 Japanese equipment companies, Ushio, Canon, Nikon, Komatsu, and Gigaphoton, and 4 semiconductor manufacturers, Toshiba, NEC, Fujitsu, and Renesas, on the industry side. For the academia side, we had Himeji Institute of Technology, Kumamoto University, Miyazaki University, and Osaka University. For this reason, the Ministry of Education, Culture, Sports, Science, and Technology, which oversees the country's universities, had to get involved. People proposed 2 possible technological approaches to producing EUV light. The first was the laser-produced plasma approach, where you fire a laser at a material to turn it into plasma, which emits EUV light. This was the approach that ASML eventually chose. The second was the discharge-produced plasma approach. You first create a cloud of material, then within that cloud, you fire off high-powered sparks between 2 electrodes to create the light-emitting plasma. EUVA researched both approaches, with the laser approach being researched at the Hirotsuka Research Center and the discharge approach being researched at the Gotemba Research Center. In this early phase, ASET also handled the EUV photoresist. The major challenge with the EUV resist has to do with EUV light's high absorbability. For traditional resist materials, the EUV light can only travel about 700 angstroms deep into the resist layer. This falls, literally, short of the 4,000 angstrom depth that the semiconductor industry is traditionally familiar with to produce their existing patterns. So the industry has to develop a new suite of technologies to accommodate. These are called thin layer imaging, or TLI. For this, ASET collaborated with the Himeji Institute of Technology. If you recall, the mask contains the chip design. ASET needed brand new subsystems for producing mirror mask blanks, which are masks without any patterns on them, adding patterns to those blanks, and cleaning those blanks' surfaces. Critically, they needed to be able to consistently produce defect-free photomasks. This is immensely difficult due to the incredible tolerances involved. ASET's intermediate but ambitious goal was just 0.1 to 1 defects for every square centimeter, but eventually they needed to get to 0.003 defects per square centimeter. Furthermore, the threshold for a defect on the mask blank is a deviance of just a few nanometers. If you want to learn more about how ASML tackled this challenge, I made an older video about it. Another reason why this is so hard is because the DUV light we previously used to detect such defects cannot penetrate deep enough into the blank's mirror layer. We need to use EUV light itself to do the inspection, the industry phrase for this being actinic light. The Ministry of Economy, Trade, and Industry decided to set up a separate organization just for this part of the EUV process, the mask and lithography-related metrology/inspection group within a research consortium called Mirai. As you might be sensing, the Japanese EUV effort rapidly expanded beyond the management capacity of a single research institution. By 2005, a critical point in the program's history, there were 4 research consortia focusing on their own part of the EUV machine. ACET handled the resist, contamination control, and making the multi-layer mirror masks. EUVA handled the exposure tool's light source as well as some of the optics. Another consortia called Leading Project handled the inter-university collaboration surrounding light sources. And finally, Mirai handled the mask defect control detection subsystems. To say the least, this was a complicated setup. In contrast, the American EUV lithography project had a single entity overseeing early commercialization, the aforementioned EUV LLC. EUV LLC went 6 years from 1997 to 2003. After which, they passed on to ASML, which took over from the American company Silicon Valley Group Lithography. By the program's end, the EUV LLC team had completed all of their objectives and had a prototype that kind of worked, the engineering test stand. The American and Japanese programs shared information with one another, so the Japanese benefited from being able to follow the Americans' footsteps towards EUV, but the Americans were clearly in the lead. In 2005, Japan's EUV development plan was for high-volume EUV lithography to hit the 45nm process node in 2010, 5 years away. Some parts of the project hit their schedules. In 2005, Mirai had already produced an actinic blank inspection tool capable of detecting EUV light scattered by blank defects. So this product was essentially ready to go. But what about the actual EUV exposure tools and their components? Everything was waiting on them. This monumental task fell onto Canon and Nikon, Japan's leading lithography makers. The two wanted to start with producing a small field prototype, kind of like a pre-alpha machine, field meaning the area of projected light. With the small field prototype, the field was just a minuscule 200 micrometers by 600 micrometers, making the device more for testing other parts of the EUV system, like the resist and the mask. For their part, the Americans of the Lawrence Livermore and Lawrence Berkeley National Laboratories, working in conjunction with Carl Zeiss, delivered this in mid-2001. Their small field device was called the Micro Exposure Tool, or MET. After this, you produce a more ambitious full field prototype, the Alpha machine. This one has a field sized at or near the production level field size of 26mm by 33mm. Starting off in 2005, Japan needed to move extremely fast. In order to stay competitive and hit the 45nm process node in 2010, 5 years away, an EUV complete system would have to be ready by 2008 or 2009. This means having a working pre-alpha machine, the aforementioned small field device, by the end of the year 2005, a working alpha tool a year later sometime in 2006, and an iteration of that alpha tool, the beta tool, ready by 2007. A very optimistic schedule, but all very necessary to catch up to ASML, which at that time was putting the finishing touches on their alpha demo tool. 2 such tools would be delivered in August 2006 to the Belgian Research Institute IMEC and the State University of New York. Between Canon and Nikon, Canon was the junior and lagging partner. When they started on their EUV efforts, they had not yet mastered 193nm immersion lithography, the most advanced technology just short of EUV. In 2006, Canon and EUVA completed their small field prototype EUV lithography tool called the SFET and installed it at an R&D center for testing. It generates EUV light by firing a 248nm krypton fluorine laser at a jet of xenon gas. At that time, the company believed they would be able to start producing their full-field 6-mirror prototype called the VS2 starting in 2009. Completion was scheduled for 2011. Canon started designing this VS2, but struggled to resolve core EUV problems like raising the EUV power level, producing defect-free masks, and extending the lifetime of the optics system. problems Nikon faced as well. This was in the midst of the global financial crisis. Canon, then the world's largest digital camera maker, was heavily affected, with profits shrinking over 60%. The company delayed plans for a new camera plant in Japan, and in 2008, total lithography R&D expense was north of $600 million a year, so the company probably decided to cut back. The market eventually recovered enough for the camera plant to move forward, but Canon never built VS2 as far as I know. It would go no further in the lithography technology chain. And as of this writing, the company still only sells KrF non-immersion, or dry, lithography systems. Nikon was ahead, though. As the world's only producer of immersion lithography other than ASML, they were Japan's lithography leader. From 2001 to 2004, Nikon worked with ASET to produce 3 iterations of their small-field prototype EUV tool nicknamed HINA for High Numerical Aperture Tool. Finally, in April 2006, Nikon felt ready enough to produce their first full-field exposure tool, a 6-mirror system called the EUV-1. This alpha device was completed and installed in the R&D Research Center at the Japanese Semiconductor Consortium SELIT, going live in January 2008. This progress was about 1.5 years behind ASML's 2006 alpha demo tool. Based on the 2005 timeline, the beta EUV device should have been done by now. But shipping EUV-1 in the first place was still a substantial achievement. Without ambiguity, we can call EUV-1 Asia's most advanced lithography machine. But it was also definitely not commercially competitive. EUV-1's late installation pushed the EUV high-volume ship schedule further back from the 45nm process node to the 32nm node. There was even talk of the 28 and 22nm process nodes. This presented a major problem because the more advanced the process node, the more power the EUV machine and its light source needed to have, and the EUV-1's light source power output was one of its biggest drawbacks. The EUV-1 used a discharge-produced plasma, or DPP contraption, produced by the Japanese lighting company Ushio and its subsidiary, the Germany-based Extreme Technologies. As I briefly mentioned earlier, the concept behind this DPP approach is to blast a lightning bolt through a vapor of xenon to generate EUV photons. The DPP approach is said to be more power efficient, be physically smaller, and supposedly cleaner than laser-produced plasma, but it struggles to output as much power as its technological competitor, and the less power the light source has, the longer the wafer needs to be exposed to that light source, slowing down throughput. The EUV-1's light source power topped out at about 100 watts. The intermediate goal was 110 to 180 watts, and the eventual goal for high-volume production was 250 watts. This would require a big system change, swapping out xenon for tin. As envisioned, this tin-based DPP EUV light source module would have 2 wheel-shaped electrodes about 20 meters in diameter lined up together. Each electrode is suspended over a bath of molten tin. When in use, the electrodes spin around such that the edges barely touch the bath's surface, picking up a layer of molten tin atoms. A low-power laser then fires rapid pulses at the wheel's edge, vaporizing the tin and forming a cloud of tin atoms floating around. The wheel electrodes then discharge a massive current that causes the cloud to collapse onto itself like a dying star, heating it up to 200,000 degrees Celsius. The collapsed tin cloud then emits EUV photons. The contraption was indeed quite nifty, but it still struggled with contamination issues as well as being able to produce enough power to become economically viable. By the time the project ended, they had not yet overcome this. ASML also tried the DPP approach themselves, but eventually halted all work on it in 2013. Power levels would not reach sufficient levels until ASML pioneered its laser double-shot method. Considering this, it is likely that Nikon would have swapped its light source over to the laser-produced plasma approach as well. The main supplier probably would have been Gigaphoton, a specialty laser maker which has been working on such a light source since 2002. Tests at SELIT conducted in partnership with Intel showed that the EUV-1 can produce beautiful vertical lines spaced between 26 and 33 nanometers wide. However, the device struggled with contamination control. UV light continually hitting the mirror's surface created carbon contamination, slowly deteriorating the mirror's reflectiveness. I am strangely reminded of this scene in one of my favorite movies, Godzilla vs. Biollante, modern-day masterpiece. Godzilla fires his atomic breath at a mirror in the flying drone Super X-2, causing contamination and damaging the mirror's reflectivity. Who knew Japanese kaiju movies were so technologically accurate? Anyway, the introduction of pure oxygen to the mirror's surfaces as well as the use of UV dry cleaning with a low-pressure mercury lamp helped clean this carbon contamination. However, the EUV team then struggled to deal with a mysterious contamination stemming from a silicon-carbon compound called siloxane. Going into 2011, Nikon's researchers were still struggling to overcome these widespread contamination issues. After the EUV-1's successful testing, Nikon would proceed on to the next EUV tool, called the EUV-2. The EUV-2 was scheduled to be completed in the 2011 to 2012 time period in time for 32 nanometers. However, it became clear that ASML was pulling ahead with a substantial lead stretching from 18 months to as much as 2 years. And with the global financial crisis in full force in 2009, Nikon cut their R&D budgets. Rumors floated around that Nikon was putting their EUV development entirely on hold. A spokesman denied it, but did clarify that the EUV-2 would remain an in-house unit. What would come out in 2012 instead would be the EUV-3. 2010 was another hard year, with market sales for lithography machines in the chip and LCD industries falling by half year over year. The company continued nevertheless presenting its internal research into 2011. That year, the company had a chart indicating that they were targeting the 16 to 11 nanometer process nodes, so about 2016. But this would be the last significant report I was able to dig up about Nikon's progress on either EUV-2 or EUV-3. In July 2012, Intel announced that it had agreed to invest up to $4 billion into ASML in exchange for a stake of up to 15%. Nikon shares fell 7% after the agreement was announced. Intel had been Nikon's second biggest customer after Samsung. The American giant is known for sourcing the lithography machines from multiple vendors, but the market evidently realized that this investment agreement meant that Intel was moving forward with ASML alone. In 2011, Nikon spent a combined 28.4 billion yen, or $355 million, on R&D and capital expenditures for its lithography technologies. Nikon probably decided that without Intel as a cornerstone customer, it was not worth spending hundreds of millions of dollars a year in R&D and capital expenditures to continue developing EUV. Quietly, Nikon's EUV efforts tailed off. EUV-3 never made its 2012 ship date. With this, ASML became the last man standing in the EUV lithography industry. Japan's EUV efforts were not totally in vain. Many component efforts turned into viable, technologically advanced businesses. For instance, we still have the actinic blank inspection tool from Mirai and its collaboration with the Japanese company Lasertec. Japanese companies also have dominant positions in the EUV photoresist space, with JSR, Shin-Etsu, and Tokyo Oka Kogyo the biggest suppliers. Japanese equipment maker Tokyo Electron also makes the equipment to apply those EUV photoresists. All that being said, however, I am sure that the Japanese would have preferred to have those $150 to $300 million EUV machines to be produced in the country as well. The story of Japan's EUV failure is utterly fascinating. I had expected a debacle, but what I found was a close race. Nikon had substantial problems with the EUV-1, but they were not deal breakers. In the end, what stopped them was economics and competition, not technology. My very rough, back-of-the-envelope calculation of the total cost of Japan's EUV effort from 1999 to 2012 is somewhere between $5 to $10 billion. This is taking into account Nikon and Canon's R&D expense over that time, the $90 million annual budgets of ASET and the 4 consortiums, and a fudge factor to account for investments made by other semiconductor makers not mentioned here. By comparison, The original VLSI project that remade Japan's semiconductor industry and spawned its lithography dominance back in the late 1970s cost about $150 million in total. So this was an exponential jump. If another government wanted to build their own independent EUV machine, for whatever reason that might be, I reckon it would likely require at least $5 to $10 billion, direct guidance and information sharing from the European and American EUV makers, and about 10 to 15 years. Something to think about. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.